for being here. We are here to talk about CEP, complex event processing, and how can it change your operations life. Both me and my colleague here are from Brazil, as are the companies that we work for, IG and Intelli. And my name is André Galvani. I work at IG as an infrastructure and operations manager.
And my name is Hubert, and I am the leader developer of the CEP product we have at Intelli.
So last year, something happened in IG that changed the way we worked. An incident occurred in our main homepage that caused an error for our users, internet users. In this situation, not just the IG main homepage wasn't available, but other sites from our portal become available too, like the sports and news and other content sites. And at the moment, no apparent cause of the error we have discovered. So 10 minutes had gone by, and all the sites still unavailable. Our monitoring system at this moment just showing to us the HTTP errors, nothing more, just single alarms. This issue was escalated for our support team that tried to solve the problem and find the solution. 20 minutes later, and no solution had been found. And what's happening? So at this moment, after 20 minutes, we just know that the problem was in the cache servers. And no solution has been applied yet. Half an hour later, and our varnish specialist was contacted to try to solve the solution, and he began a thorough investigation. Almost an hour later, he found the problem in our varnish servers. The problem was, there is a kernel model called the IP contract that is responsible for some networking functionalities like NAT and stateful IP tables release and stateful inspection, packet inspection, and so on. So this model is responsible for store all the connection state in the memory. So when you have a server that holds a lot of connections, normally you consume a lot of memory too. And to difficult our resolution of the problem, this model was just enabled in one of the servers, cache servers. So it was even harder to find the solution. And there is a variable in this model called IP contract max that controls the maximum number of connections of this model. So when you have a lot of connections coming in the server, normally in the default variable reaches off the maximum very quickly. That's what happened with us. When this variable reaches the maximum number, all the connections start to be rejected. So when it happened with us, all the users start to see error in our main homepage and other sites too. So in my view, as a manager, this incident brought to us a lot of problems. In a technical, in a business perspective, we had some situations. In a technical perspective, my team waste a lot of time to find a solution, try to solve the problem. So in a classical monitoring systems, it's very difficult to find a solution very quickly when you have this kind of problem, because it was very difficult to understand if you have few informations to try it. And this kind of state reflects the inability to classical monitoring when you just have some few informations to find the solution. If you had preventing monitoring systems like predictive systems, probably the solution was detected and solved very quickly. In a business perspective, we had our credibility and the image affected because when a user enters your website to see your content and get all the information and see an error, it's very bad for us. And also just the image and the credibility. You lose a lot of money too. In our situation, almost an hour of downtime, we lose a lot of money in ads because when you have a portal, normally you sell banners and normally you have e-commerce websites related. So we lose a lot of money in this situation here. In the classical IT monitoring systems, we have some situations here. Normally, we have single variable alarms that represents nothing for you, because you just have HTTP alarm, and what it is? Nothing. It's difficult to find the solution. Normally, you have spread out data, and when you have HTTP error in one system, you have a high load in another system. It's very difficult to put all together. So it's not useful. And normally you have reactive systems when just when the problem occurs. Is not acceptable today because when you sell banners and sell products in your website, you have 45 minutes downtime. Is very bad for your business. And operations can be better. You can improve it, you can change it, and and we did it. So there is a lot of ways to do that. In a classical monitoring system, you have some missing things. No problem prevention is one of them. Error anomaly detection, more efficient data analysis, and learn from the past. It's very important to learn from the past. We learn from the past in a hard way here. So when you have a problem, try to implement this to not happen anymore. And more intelligent monitoring systems, you have to pay attention for these three things here. Real-time data analysis, it could improve and give more power for your operators. Collaboration among sysadmins and developers. You can put all together to collaborate in the monitoring. And simplicity. Your operators think if you keep all the information simple, because if you create a very, very difficult and monitoring systems is not so good for the sysadmins or the operators handle it. So keep it simple. So how can you avoid this kind of problem? How can you improve it? How can you change this kind of situations in your infrastructure or in your systems or in your environments? My friend here, Hubert, will demonstrate some solutions here that can you use to change this situation, and you are applying this in our environment too.
Thank you. So, how can we early detect the common problems, or even how can we avoid them from happening? We've built a product in which we use complex event processing technology to implement what we call scenario-based monitoring. That is, describing scenarios using expressions that would reflect real problems, common problems, or threatening situations, or even opportunities to act. Complex event processing is a technology based on data streams. It's useful every time that there is a situation with high frequency real-time and a need for real-time data analysis. Such applications, there are such examples as financial, trading, telecommunication systems, and other where the traffic is very high. The volume of data transferred is very high, and there is a need to analyze it in real time. In a common database, the data is still while the queries are passing through it. The data is indexed and the queries are passing through it, and every time a query passes through it, there is an output, a data output that represents what this statement wants to have. Inverting the logic in a complex event processing based systems, the statements are indexed and the data is passing through. And every time that a condition described in one of these statements is reached, then an output, a data output is given for that situation. It's like an inverse, it's an analogy with a common database to describe better what is it. The data stream is described as a sequence of events in the time. An event is an immutable register of an action, for example, a measurement, or of a state change. Here is an example of a measurement, an example of a metric, and every event has properties that describe itself. Here there are 5 properties. The timestamp properties describe when the event was generated. The HTTP, the event type property describes its type, which is HTTP here. The host property could be any other one, describes where this event came from. And there were 2 metrics. There was response time, for example, 0.1 seconds, and the status code of this metric. We use Asper in our solution that is developed by Aspertech, and Asper introduced a DSL called Event Processing Language that is a descriptive language, and it's simple and powerful to describe the scenarios in which we're interested to detect. Here's an example. Select asterisk from HTTP. The asterisk means which properties I'm interested on the output. The HTTP represents the stream in which I am interested. There is an event type, for example, called HTTP, all2, and the stream HTTP is defined by the sequence of events of type HTTP. So whenever an event of type HTTP arrives at the engine, there will be an output, there will be generated an output, which is the HTTP events properties. When the first event arrives at the engine, the output would be its properties. When the second event arrives at the engine, the output will be the second event's properties. And how can we use that in practice? Measuring availability from outside the data center infrastructure is a very common practice. It's useful when you want to know the latency or the response time that the users are really getting from your sites. So you can measure the availability from different parts of the world, and for each measurement, you want to know what is the response time for that measurement. And you want to be notified every time that the response time is too high or every time that there is an error on this request. So you could make requests from different parts of the world and describe the scenario that you are interested in. This statement describes the scenario. Here, we use a simple statement, select site and origin from HTTP. So for every event of type HTTP that arrives at the engine, there would be an output for this statement that would be a new event with the site and the origin information. The site is the site which is being measured, which response time is being measured, and the origin is from where this measure came. And we want to be notified only if the status code of the request is greater or equal 400, or the response time of the request is greater than 3 seconds. And what do we do with this? we can create, use the insert into statement to define a new event type or a new stream, which every time that this condition is reached, there will be generated a new event of type request error that would go to the engine again and could be processed by itself, or it could generate an alert. There is another keyword in event processing language, that's the pattern keyword. This expression, select asterisk from pattern A followed by B, where the followed by is represented by the 0, would work this way. There are 4 events there. The two red ones represents events of type A, and the 2 blue ones represents events of type B. So whenever an event of type B arrives at the engine following an event of type A, I want to be notified, or this statement will have an output. When the first event arrives at the engine, there will be no output for this statement. When the second event arrives, there will be no output either. But when the third event arrives, it is a B event type. And the previous event was an event of type A, and then this output would generate, this statement would generate an output, which is the B1 event's properties. And we could use this statement to detect, to improve a little bit the example I have shown before. In the last example, we are notified every time that a measurement detects any kind of error. But when I am measuring availability from outside, the problem may be in the data center infrastructure, they shall be inside or the data center, or can be an external problem, can be a problem on a link of a provider. And this problem on the link of an external provider would cause the measurement to alert. And I can improve the statement. Although I want to be notified if there is an external problem, I want to be notified more when there is an internal problem. And to detect that there is an internal problem, I only want to be notified if there are 2 or more simultaneous failures in distinct links. And how can I do that? I can use the event the stream that I defined in the last sentence, which is request error, and using this stream, I can use the keyword pattern to describe a pattern where there is an event of type request error, which I attribute to the variable A here, followed by another event of request error, which I attribute to the variable B. But I only want to be notified if the origin of the second event is different from the origin of the first event. That is, I only want to be notified if the problem is repeating in different links. And these may represent an error inside my infrastructure. And I only want these notifications to occur if both events arrive within an interval of 5 minutes. The event processing language also defines the windows. Here's an example of a time window. I want the output to be the average of the property P of all the events that are within this window. That is, assuming that the events are arriving at a rate of 1 event per 5 minutes, when the first event arrives, the output for this statement would be the property P of it. When the second event arrives 5 minutes later, the output would be the average between the first event and the second event's P properties. But 15 minutes later, when the third event arrives, the first event is not in the window anymore. So the output would be a moving average between the second event and the third event's P property. It is very useful to detect, for example, an unbalanced web server, which is, there is a farm processing web requests, and there are several servers processing web requests, and when one of these servers starts to process more than the average of the number of requests on all the farm, in the whole farm, there could be a problem. It could be a problem in the configuration, or it could be a problem, a possible attack, for example. If my network balancing algorithm is defined by the network hash, if somebody attacks me from a single IP, all these requests would be processed by the same server. On the other hand, if there is a server processing less than half than the average of the whole farm, there could be also a problem in the configuration of the balancing algorithm. So this statement would represent the situation in which we are interested in the host sessions stream. And from this host session stream, we want to be notified of the host and the number of sessions, which I described with this s_num property. And we also want to know the average of this number of sessions within a time window of 10 minutes. And we can be notified every time that the number of sessions is more than twice the average of the number of sessions in the farm, or if the number of sessions is less than half the number of sessions in the farm. And one more example, there is also the fixed length window. Here the window is a fixed length on 2 events, and the window is over the stream HTTP. And there is an operator like the average operator, which is the previous operator that would output the previous P property event. When the first event arrives at the engine, the output will be null because there is no previous event. And when the second event arrives at the engine, the output is the P property of the previous event, and so on. And this previous operator is very useful to measure an increase in the number of connections at the backend, which could mean that the front end is not processing the requests correctly. It has occurred when there was an infrastructure that was kept from one version of the product to the other version, and there was some web page links that weren't supposed to exist anymore, but somebody has forgotten to remove these links. And then every time any user clicked on one of these links, the front end, which was supposed to respond with a 404 error, wasn't responding. It was passing the request to the backend, and the backend was processing 404 errors. And this could be an open door to a possible denial of service attack, for example. And as it's a very common situation, it's very common also to detect it. This statement compares the number of connections, of TCP connections, with the previous number of connections. We define the event type TCP, and we make a select on the stream TCP, and we want these 4 properties: the host, the IP, the port, and time wait count. It's very difficult to measure how many connections, how many TCP connections are there in an active state. So we measure the connections in a time wait state. Although it's not the same, it must be proportional one to another. So an increase of connections in an active state would lead to an increase of connections in the time wait state. And it's easier to measure the connections in a time wait state. And we want to use the window of the time window over a group window, which means I want to keep the 2 minutes last events for each group IP and port. And then I can compare the number of connections, of TCP connections on any server with the previous number of connections for the same IP and port. And this output would, and this statement would output every time this condition is reached, which could mean that the front end is not processing the connections correctly. Another situation, the back end could have been crashed, or the link between the front end and the back end could have been lost, for example, And this situation, this statement would describe the situation and would alert every time that it occurs. We correlate here the information of the load balancer servers and the front end servers. And every time there is a increase, a growth of 30% in the number of sessions on the load balancer associated to an error of timeout in the front end, then there must be a problem. Because when the front end, the back end is not processing the request, the front end starts to accumulate the requests and would start to time out these requests after some time. And if the timeouts error are associated with a growth in the number of sessions, there probably may be a problem in the communication of between the front end and the back end. And there are many other examples that I want to show, but it's easy to make the operators and the engineers and the developers collaborate describing these scenarios. And these scenarios are automated, and they run every time, and every time one of the conditions is reached, there may be output an alert or even an action that would act to try to resolve that problem. We not only monitor these situations, but we try to correlate any of these situations with possible root causes to that problem. We can measure the symptoms, but we can't measure the causes. The causes we try to discover looking at the symptoms. There are some different symptoms. There are near 100 of different scenarios created based on common problems, and these scenarios can be created by the users. There is a web interface which the user can create new scenarios or can update existing scenarios. At runtime, although it can be easy for a developer, it's easy for an operator if he has something to look at and try to make something similar. And it makes easier to people contribute by one updating the scenario that other has created. And there is also an easy way to backtest the scenarios. You can resend the events of the past to the engine again without affecting the real-time statements. We can isolate another service and send it again and replay the past events, and would know the output that would have been given if the scenario existed in the past. And the product is very easy to integrate to. It talks many protocols and many formats, and we write the modules in many different languages too. So it may work as a second tier of monitoring. There can exist together the first tier of monitoring system, which describes the collectors. And the collectors could send information to the correlation engine, and from the correlation engine we can describe these scenarios and be alerted whenever every time anything goes wrong, or use this correlated information to create charts that are more meaningful since they have aggregated information and correlated information on it. So we don't need to look at 100 charts, but we can look to one chart that correlates every important information from every different source that you want. And we've been working with complex event processing on IT monitoring for 3 years. We won last year the best paper award in the Associations of Computer Machinery that describes what is the implementation of what's considered the state-of-the-art in anomaly detection algorithms. And we also published a paper in Distributed Event-Based Systems Symposium last year. And we are partners of, we use Jasper, which is developed by Aspertech, and we are part of the Event Processing Technical Society too. And we not only use complex event processing to describe the scenarios, but we also use it as a preprocessor for machine learning algorithms, for example, where we can aggregate the information before sending it to the algorithm to decrease the size, the amount of data that we are sending to the algorithm to make it easier to the algorithms to perform their calculations, or to aggregate the information before sending it. There are several usages like that. We use for visualization to make more meaningful and simpler charts and to make several dashboards that correlates information from different sources. And we created what we call the live troubleshooting that associates the symptoms that we can measure using these scenarios to possible causes of any problem. When a condition is reached of one of any of the scenarios that I have shown, there are some possible causes associated to these conditions, and when one or more conditions are reached, it is easier to detect which cause is, which symptom is related to each cause on a common problem. And the system defines a monitoring information bus in which all the collectors send the data, send the information, send the events, and these collectors could be infrastructure collectors, like could be this, CPU measurements, memory measurements, or HTTP, or the number of sessions in the load balancer, or even business metrics too. So we can correlate all this information, and this information would be processed by the complex event processing engine, and the CEP engine would also act as an input to other modules, the visualization module, the machine learning module, or the storage module. We store all the data that arrive at the engine, and this corresponds to near 1,000 events per second, and all of this is stored to later analysis, and it's very useful to analyze it later. And by the way, the problem that André Galvani has shown in the beginning of the presentation, after it occurred, we created this statement that correlates the number of sessions in the load balancer with the number of drops in the cache connections. So every time that the number of sessions decreases by 30% compared to the average of the number of the sessions in the whole varnish farm, and the number of connection drops in the cache server in the last 5 minutes, which represented by this variable, this property drops, is greater than 0, the are happening connection drops, we generate an alert that could be probably related to the problem of the IP contract module. Could be related also to other problems, and there will be a list of possible root causes of this problem. But it makes it very easier to detect a problem. And we can detect the problem in a time window of 5 minutes. So we can detect this decrease in the number of sessions in 5 minutes, and rapidly know where to act and where to look at. And we output this statement. We control the output rate of this statement in 15 minutes to avoid flood of alerts. So we generate only one alert that's possibly related to this cause, and the second alert is generated only 15 minutes later, but 15 minutes later, probably the problem was already solved. And the event comes with the information of the VIPs, the number of sessions in the load balancer, and the number of connection drops in the cache server. And we also extended a little bit the DSL described by Esper with that function in Node that would filter the cache stream only to filter the input, only to make an input to this statement where the node variable of each event is equal to the string static. And after this,
just let me make a question here. Have somebody here have the same problem I showed before with the IP contract model and the cache servers using Varnish? No? Okay. It's fine.
It was not easy to detect the problem.
Yes.
So 45 minutes to detect a problem is unacceptable. And as we grow the number of these different statements and we grow the knowledge base, we have easier is to find a common problem, a problem somebody has already challenged. And after that, the problem occurred again in 4 different occasions. And in any of them, the downtime of a part of the infrastructure was more than 10 minutes. Okay. So, thank you very much.
Thank you. We have 10 minutes for questions.
If anybody has a question.
Questions?
Okay. Mostly, the most parts of the infrastructure, the data centers already have infrastructure of monitoring. They already have Nagios, for example, or Cacti, or some system that makes what we call the first tier of monitoring. And we've written, for example, a plugin to Nagios to detect, to catch all the information. We make a trapping on all measurement that it makes, and this plugin sends by Stomp the information to a broker that's written in Java, and this broker would notify our system of this information. There is also some scripts that we make to collect information. There are scripts that collect metrics that they ask every 1 minute, for example, for some specific information or some specific properties. Or there are scenarios where we are interested in some state change. Or every time the server is going to be shut down, then alert me. And then I will change a snapshot of the system now. And so I know that this server is shut down. And whenever it turns on again, then alert me again. There are two types of these events. And the most common approach is to write these plugins and these scripts to send the data to the engine. And at the engine, we must know in which format this data is coming. We must know what is an HTTP event, what is like, which information it has on it. We have to know the static type of these events. And based on the static type, we can create these statements that we try to keep with the same names. For example, the CPU event, we know that comes with the load information, and the idle in the system, it comes from Nagios. But if it comes from collectd, the information is a little bit different. So we have to create this knowledge base over the formats that are already known by the monitoring systems that we know. And then we can correlate this information that comes from different monitoring systems and take a little bit more from it. Sorry? Yeah. Splunk started as a log monitoring tool and recently changed it to a real-time and complex event processing approach. We've started on the other side. We've started as a complex event processing tool, and now we are looking for the log information. So we are very used to not to full text search or not to text information. We have something made analyzing text, but we analyze mostly numbers. We analyze time series. And it's a different approach. I think they will converge, but our goal, our aim is to show the information and to detect patterns on this log at real time. And the other hand, I think Splunk has a way to make a search or make a query and try to analyze a post-mortem situation, not try to prevent a situation. Our goal is more to prevent or to early detect than to post-analyze this information. And for curiosity, I have here an example of, as we are talking of data series, we have developed this algorithm that already existed in the financial market. It's called perceptually important points. We call it PIP. And the PIP is an algorithm that chooses in a time series which are the most important points that if they are plotted, the chart would be the more similar to the original chart if the millions of points were plotted. So we can preserve the resolution in 1 month of information, and we can see, for example, a peak that occurred 4 days ago, or a valley that occurred 7 days ago, and the chart is almost the same, or is the same as if we have plotted 1 million points. There are 300 points here on each chart. So we have made some effort to analyze time series data and to analyze time series behavior. The algorithm we have developed is to detect an anomaly in time series behavior on time, and we can analyze, we can correlate 50 different variables and in their eigenvalues, and then and try to reconstruct the signal on every new sample that arrives at the system. And if the reconstruction error of the signal compared to the actual signal is more than, for example, 1%, then we generate an alert telling, oh, there must be a problem on that signal, that must be a problem on that server, take a look on it. And then this event, take a look on it, could come back to our engine and then generate an alert based on it. So our approach is more on numbers, on time series, and on early detecting and preventing, than more on an analysis view. Anyone? So, thank you very much for being here. Hope you have enjoyed.
Okay, thank you.